So first of all, let's mute all the participants who is not Peter. Mute all, continue, unmute Peter, that's good. And so welcome to the afternoon or evening, morning, I don't know, second half of our conference, afternoon session. And so the main idea of this online conference is that you get to listen to wonderful talks, but also you're very welcome to ask questions. To do this, you can either raise hand and then the chair, who is me, will tell you, hey, you're welcome to ask your question, and then you unmute yourself and ask a question. Or if for some reason you're uncomfortable asking a question with your voice, you can write it in the chat and then I will read it out to the speaker. Please be welcome to ask questions. We have talks which last 1 hour, 15 minutes, because we took into account that asking questions this way takes some time, so please feel welcome to do so. And so our speaker is Peter Haine from MIT. Peter is a PhD student of a ghost of Clark Barwick, because Clark is in Edinburgh. Well, right now in MSRI. I mean, it's complicated, but Peter is at MIT, gonna graduate next year. And we're gonna listen today about stratified Étale homotopy theory.
Yeah, so yeah, this is really kind of the whatnot part of the motives and whatnot. And I should say, for people in Regensburg, this is not the same talk that I gave a couple of weeks ago. So it might still be interesting to you. And it also is not on something that was contained in the paper when you ran a seminar on it a bit ago. So stay tuned. Okay. So I want to start by recalling a few things about sort of how Étale homotopy theory works. So, well, so I'm going to recall some things about ℓ-1 Étale and also about Étale homotopy theory in general. So probably most people are familiar with ℓ-1 Étale, but maybe not sort of how Étale homotopy theory works. So throughout, S is going to be a scheme, and S bar mapping to S will be a geometric point. And oh yeah, I should also say, if I start not noticing writing below where is visible, please let me know. So okay, let's recall some things about Étale ℓ-1. So this was, something that Grothendieck cooked up a very long time ago, and is now very standard. That's supposed to sort of be the Étale version of fundamental groups from algebraic topology. So what type of object is this? Étale ℓ-1. It's a pro-finite group. So it's a pro object in the category of finite groups. Often we just think about it as a certain type of topological group. Because of stone duality, you're able to regard profinite groups as topological groups where the underlying topological space is compact Hausdorff and totally disconnected, also known as a profinite set. Well, one type of profinite group that arises in algebra a lot is Galois groups, and so this is supposed to generalize Galois groups. So if you take ℓ-1 at a speck of a field at a separable closure, it recovers the absolute Galois group as a profinite group. There's a sort of comparison to the complex world. So if you have, well, if S is over C and it's of finite type, so we can reasonably talk about the corresponding analytic space, then, well, there's a map from the usual pi1 of the complex points in the analytic topology to pi1 étale. And well, it's not an isomorphism because this is some profinite group. This is just some group, but it becomes an isomorphism after profinite completion. So this is often known as Riemann existence. This is some sort of generalization of the classical Riemann existence theorem. And then maybe part of the most important part of this is that like in topology, this group actually classifies locally constant sheaves as long as you have some finiteness conditions. So let me just say it this way. So if S is connected, because I mean, I'm choosing a point, so if I want this to classify everything, it should be connected. Then, well, locally constant constructible Étale sheaves, say of sets on S, these are classified by pi1 étale. So what does this mean? So locally constant constructible, this means that, well, they're locally constant, and I can choose a cover that only has finitely many elements in it, so that they're all, when I trivialize over that cover, it's constant with finite at a finite set, or constant with finite stocks. So these are classified by sort of representations of this pi1 étale. So one way of saying that is they're classified by finite sets with continuous action of this group. And so this is what you might call the monodromy equivalence here. And okay, so basically Étale homotopy theory is designed to do the same sort of thing, except to allow you to define higher Étale homotopy groups. So how does this work? Well, today I'm not really going to I'm not going to tell you so much about how to define the Étale homotopy type, though I'll explain a new definition of it. But let me just tell you sort of how the theory generalizes and what Étale homotopy theory is designed to do. So, well, what you would like is to associate, well, instead of a profinite group, a profinite space. So I'm going to put a hat to remind myself that it's a profinite space. I'll call it pi infinity at hat of S. This is going to be a pro object in finite spaces, pi finite spaces. So this is the infinity category of pi finite spaces. So these are, well, one sort of higher categorical or higher homotopical analog of finite sets. they're spaces that are truncated and all of their homotopy sets are finite. So they have finitely many connected components, and all of the homotopy groups at every point are finite. And they eventually vanish above some degree. And well, maybe to say an analog of this fact will be, if you have such a finite space, then you can take its homotopy groups, and well, it turns out that in this setting, it makes sense to take it with respect to a geometric point, and this recovers Grothendieck's Étale pi 1. But in general, this is not n truncated for any n. It has some higher homotopy. Again, there's a sort of Riemann existence theorem, which is that if you have a finite type scheme over the complex numbers, then, well, what can you do? Well, there's a comparison between sort of the underlying homotopy type of the complex points in the analytic topology. There's a comparison between that and this profinite space that's the Étale homotopy type. But, well, of course, again, it's not going to be an equivalence. This is just some space. This is some profinite space. But it's an equivalence after profinite completion. So I'll write it like that. It becomes an equivalence after profinite completion. Okay, and what's the analog of this? Well, basically, it's just that you replace sets by spaces. So let me maybe write it this way. I'll write LCC et of S for the infinity category of locally constant constructible sheaves of spaces. So it's defined in exactly the same way. You look at Étale sheaves that can be trivialized over a finite cover, and they're constant with values a pi finite space. So this is the higher categorical analog of locally constant constructible sheaves of sets or abelian groups. And well, another way of saying representations, usually you say if, this group is just a group and not a profinite group, you say it's, functors from the one object category with automorphisms that group to wherever. And well, you can say the same sort of thing. So it's functors from this profinite Étale homotopy type to the infinity category of pi finite spaces. But let me put a little CTS for continuous here to mean that what this means is, well, it makes sense to take, spaces infinity groupoids, and I can take functors from some infinity groupoid to pi finite spaces, and that gives me some infinity category. And what this CTS means is just you extend this to the category of pro objects in sort of the way that you have to. So remember, the category of pro objects in some category, that's obtained by universally adjoining all co-filtered limits. So it's sort of dual to end objects. So you want to extend this, in the unique way that, well, since I put ops everywhere, it should send co-filtered limits here to filtered co-limits in categories. So it's that extension. So, I mean, in some sense, it's almost a functor category, but not quite. But this is, the usual situation that we're in algebraic geometry. where we have to contend with pro objects. And so today's talk, what it's going to be about is about two modifications to the story. So the first modification is going to be about removing the local constancy hypotheses. So it turns out that this profinite Étale homotopy type like this can actually be defined by this equivalence. So this is something I won't go into today, but there's this really wonderful story of shape theory and profinite shape theory due to Jacob Lurie. And the Étale homotopy type can actually be defined via this equivalence. But often sheaves that you think about are not necessarily locally constant constructible, but are just constructible and without the local constancy. So today's talk is going to be about removing this local constancy hypotheses. And well, here I didn't explain what this profinite Étale homotopy type is. And part of the reason is because in some sense, it's not so explicit. It's some profinite space, and it's there are various nice ways of defining it, but it's kind of hard to identify. And one of the sort of nice things about this is that it will turn out that the object classifying constructible sheaves has a simple description. And so it'll turn out to be a pro-ordinary category. There's no infinity involved here. And then the second part will be what has to do with condensed mathematics. And that will be extending from finite coefficients to L-adic coefficients.
Peter, so do I rightly understand that in the first, like when you remove local constancy, you also say something new about the classical story, right?
Yeah, you also see something new about the classical story. So yeah, yeah, if you say, well, maybe you're kind of upset because I didn't tell you what this Étale homotopy type is. This will also give a new definition of the classical thing. So that's kind of nice. And I mean, part of the hope is that that new definition will actually be useful. Okay.
Thank you.
So so I'm going to move on to the next page here. Okay. So this, I'm going to start talking about the story of stratified Étale homotopy theory. And there are many different ways of telling this story, but I've chosen one that I think is, going to hopefully be efficient for the purposes of this talk, but there are lots of different ways in which you can sort of arrive at the same thing. But I want to make the sort of suggestive observation to start, which is, so first, let me recall something. So let F be an Étale sheaf. Let's just say of sets, it doesn't really matter, on a scheme S. And let's choose 2 points, 2 geometric points, S bar and eta bar, geometric points. Such that the point S, so the the image that this picks out, it's in the closure of the underlying point of the scheme that eta bar picks out. Okay, and the thing that I want to recall is that every sort of Étale specialization. So this means that S is the specialization of eta. Sort of, for topological spaces, specialization just means, that you're in the closure of some other point. But if you want to talk about a specialization of sort of geometric points in the Étale topology, the right way of saying that is that you're choosing a lift. So you have your point eta bar mapping in here, and you can look at the spectrum of the strict tensillization of the local ring. So that's sort of the infinitesimal neighborhood of the point little s in the Étale topology. And for every lift of this point to this infinitesimal neighborhood, this gives rise to a specialization map let's call it SP sub alpha, from the stock of your sheaf at S bar to the stock of the sheaf at eta bar. So it gives rise to a map like that. And remember, the stock of the sheaf at S bar, another way of saying it is you pull back the sheaf to here and then you take global section. So it's not so hard to define this map, but let me not do it because it won't be so important. But the important point is the following, is that if F is constructible, so remember, this means that there exists some sort of finite stratification of the scheme on which each piece, it's locally constant constructible. Then F is locally constant constructible if and only if all specialization maps are equivalences. Meaning, whenever I'm in this situation of this observation, this map is an equivalence. Okay, so what that suggests is that maybe there's some way of reconstructing your sheaf by knowing all of its stocks, knowing all of the specializations, knowing sort of the actions of the Galois groups on the stocks, and piecing them together in some way. So so what are we going to need? Well, in general, these things won't be isomorphisms like they are in the locally constant case. So we're going to need, if we want one of these classification results that says basically functors out of some gadget to pi finite spaces or constructible sheaves, we'll need to replace this profinite Étale homotopy type of S by a pro category, gal S is what we're going to call it. And somehow the amazing thing about this is that you may think, I mean, this generally is not usually truncated. It can have all sorts of higher homotopy, though there's some amazing recent results of Piotr Aschinger that say, you know, in positive characteristic, actually often this is one truncated, which is pretty surprising. So really the Étale fundamental group knows everything, but this object that I'm about to define for you, this will be a pro one category. And so it'll admit a very sort of classical description. Yeah, so really this guy, which we call gal S, or the Galois category. I know the Galois category is already a used term, but it seemed appropriate, as you'll see in a minute. So this will be a pro object in one categories with finitely many morphisms and the theorem will be that constructible Étale sheaves on S are the same thing as functors in this pro sense, which means that if you represented this category as a co-filtered limit, this pro category as a co-filtered limit, you'd pull it out as a co-limit, satisfying this sort of classification result. But how I'm going to describe this to you.
Hey, there is a question. Could you please repeat? Why do you need to replace the Étale homotopy type with the pro category?
To classify constructible sheaves?
Mm-hmm.
Yeah. Is this the question?
Why do you need to replace?
If you want to classify constructible sheaves, basically the reason is because these specialization maps are not going to be equivalences. So you somehow, you know, how you should think about this is, I mean, this is kind of a bit hard to get a handle on, but somehow, well, one thing we'll see later is you can actually describe this basically as having objects, geometric points of your scheme, and then a bunch of equivalences, you know, between these objects that are kind of hard to describe in general. And that's because locally constant constructible sheaves, all of these specialization maps are equivalences. But without the local constancy, they're not equivalences. So like, you know, for example, if you had a DVR, you know, so it has these 2 points and you're looking at the stocks at each point, you have this specialization map, but it's not an equivalence. I don't know if that answers the question.
Yeah, okay. I guess I'm still myself a bit confused. So since why do you want them to be equivalences at all if you look at non-local constant things?
Yeah, so we don't want them to be equivalences. Okay. So that's why it's going to be a category, because not all the morphisms will be equivalences.
Ah, okay, I see. Thank you.
Yeah. No, thank you for the question. So what we'll do is we'll really define a category object in profinite sets and it turns out that you can regard this as a pro-category. Really, this comes from some much more complicated construction, but there's a sort of simple version that is relevant. So okay, so let's get on to the definition. So here's how it works. So this will be a definition that will work for QC-QS scheme. So S will be a QC-QS scheme. And so the pro category, which I'm going to describe, as some category object in profinite sets, gal S, well, it's going to have underlying category sort of the category without a topology, the category of points of the Étale topos of S. So what that is basically is just a bunch of, it encodes the data of the geometric points, and it will encode the data of these specializations. So this is sort of why I wanted to bring this up, is it sort of suggests what you might try to do. So Grothendieck computed what this is. So its objects are geometric points S bar to S. So, by this, I really want to mean that the residue field of this S bar is going to be a separable closure of the residue field of its image. And then the morphisms, well, there are a couple of ways of describing this, but I want to describe it in the same way that I described this up here, is that there are these specializations in the Étale topology. In the Étale topology. So let me try to use the same notation as before. So the morphisms in this category from S bar to eta bar, they're going to be defined to be the set of lifts of the geometric point eta bar to the strict local ring, the local ring in the Étale topology at the other point. So in order for this to be non-empty, S has to be in the closure of the point eta. So that hypothesis that I had before was not really necessary. So I'll say a bit more about this in a second, but let me.
Sure, there's a question.
Yes.
Could you please say a couple of words of how do you go from pro category to its underlying category?
Yeah. So you take the limit. So does that make sense to the answer or the?
If I'm allowed to think of a pro category as a limit of categories, then yes.
Yeah. So I mean, okay. So let me write a little aside thing here. So one thing that you can do is say you have a category and you look at pro categories. There's a Yoneda embedding like this that embeds categories into pro categories. So if you think about them as sort of, formal inverse systems, this is just the constant ones. And that functor has a right adjoint that you can think about it as sort of taking the limit. It's often called materialization. That's not really something that's specific to categories. That it's also true for pro spaces, in a lot of generality. But yeah, so this constant thing, that's part of the universal property. You have to have such an embedding. And then if you already have inverse limits, by the universal property, you get the functor this way. Yeah. So, okay. But yeah, it turns out in the case of interest, this can just be described as sort of a category with a topology. And so, okay, here's a key remark. Before I describe the topology, the key remark is that if you look at morphisms in this, well, now I haven't described it with a topology yet. So in this category of points from S bar to S bar, this is isomorphic to the Galois group of S bar over its image point. And so this was a separable closure of the image. So this is the absolute Galois group of the residue field. So, maybe this suggests that if you just had this category of points, you could globalize sort of the topology on the Galois groups to get a topology on the category. And essentially, that's what I want to do. So I want to describe how you could endow the Hom sets with a profinite structure and regard them as profinite sets. So where's the profinite structure? Where does this come from? Well, so the thing that I want to say is, okay, so if you had not thought about this local ring in the Étale topology, so this strict Henselization of the usual local ring, if you have not thought about that before, then there's a convenient way of thinking about it that's going to be important from this perspective. So it really is a sort of infinitesimal neighborhood, as much as that makes sense, of the point that you pick out in the following sense. So you can write this as a limit of U, where you're looking at a diagram of maps equipped with a lift of this point, where this map, well, you don't have to be so restrictive, but let me just say it's affine Étale. So you can look at.
Okay, sorry. May I interrupt you for a sec and ask, so this Q remark, does it follow immediately from the construction, or there is some deep anything?
No, I don't think there's some deep anything. Maybe, I mean, one thing to say is that this can also be described in a second way, which is also useful, which is that it's morphisms of S schemes from the strict localization at the point eta to the point S. So from that, it's easy to see. Yeah, it's somehow, no, it's not really a hard fact.
Okay. Sorry for interrupting.
Yeah. Oh, no worries. But it's, yeah, somehow it's important. So yeah, you can actually think about this as, a sort of, let me just say equals in quotation marks, because this doesn't really make sense. So you think about it as, this kind of gadget, an Étale map down to your scheme along with a lift of the geometric point. That's called an Étale neighborhood. so it's sort of an intersection of Étale neighborhoods U of S bar of U. So somehow that's how you should think about it. But of course, this is not going to like be open in your scheme or something like that. It just has a map down to it. And the other key remark is that this diagram is co-filtered. So it suggests that you should, you might be able to regard this set of morphisms as some profinite set by pulling a limit out. So where the profinite structure comes from is, well, you look at the morphisms here, and well, what are those? So they're morphisms of S schemes from eta bar to this guy here. Okay, and well, you regard this guy as that, so you pull the limit out. And let me just write lim U of morphisms of S schemes from eta bar to U. And of course, you can, if this is supposed to live, be a lift, you can write this as morphisms from eta bar, and it has to, hit the fiber.
Can you lift the paper, please?
Oh, yeah. It has to hit the fiber over your point, and this is going to be some disjoint union of spectra of finite separable extensions. And that's where the profinite structure comes from. So you can endow this with the structure of a profinite set.
Can I, do you mean U eta?
U eta, yes, thanks. Yeah, I changed the notation from my notes. So I mean, this is not a complete description, but this is sort of gives you a flavor of where it comes from. And so really this construction, in the work with Clark and Saul, we construct it in a different way, in a way that uses a ton of machinery, but this category, but then it turns out that it can be described in a sort of classical way. And so now what I can do is I can actually give you a description of the Étale homotopy type. So here's a description of the Étale homotopy type. So this is something that is due to me, is that, so again, S is a QCQS scheme. The thing is that there's a natural morphism of prospaces. So, okay, as it turns out, there's a sort of non-profinitely complete version of the Étale homotopy type. So I'll write this without a hat. And the profinitely complete version is the profinite completion. So this is some object in the infinity category of pro spaces. But unfortunately, in some sense, its behavior is not as nice as its profinite completion. But it profinitely completes to this profinite Étale homotopy type that I described before. And then, well, we have this pro category that I described above, gal S. And, well, if you invert all morphisms in the pro sense, so this B, this is going to go from pro objects in infinity categories to pro objects in spaces. This is the left adjoint to inclusion. So it's just sort of, if you think about this as some co-filtered system of infinity categories here, I mean, you're basically just sort of inverting things level-wise, is how you should think of this. I mean, that's not quite accurate, but it doesn't lead you too far astray. So if you invert everything in that sense, then this is an equivalence on homotopy pro groups. So yeah, somehow for exactly the same reason that Vova was saying in the last talk, that equivalence on homotopy pro systems for homotopy groups of pro spectra is not the same as being an equivalence. It's true for pro spaces, but anything that basically anyone has ever said about pro spaces was after inverting these equivalences on homotopy pro groups. So this gives you a new way of thinking about the Étale homotopy type. You can think about it as you take this construction that somehow you could make sense of classically if you wanted, that I tried to describe here, and then you invert all morphisms, but you have to do it in this pro sense. So, okay, that's kind of nice. And let's get to where constructible sheaves are involved.
So do I understand correctly that a priori right-hand side is much simpler than left-hand side, or much more explicit?
Yeah, a priori it's much more explicit. So the definitions of this side, I mean, there are sort of, well, yeah, there are a couple. I mean, there's a classical definition due to Artin and Mazur and refined by Friedlander that uses hypercovers. That's somewhat complicated. There's a definition using shape theory of Lurie that's really elegant, but kind of inexplicit. So this has the benefit of being explicit, but maybe it doesn't make it that much easier to compute. But there are some useful kind of facts about this, which, like, one of the kind of interesting things that happens in this is that if you take this Galois thing applied to one of these strict tensorial local rings, it just produces an over category, or maybe it's an under category. Well, anyway, it's either an over or under category under that geometric point. So there are some kind of surprising things that you can get out of this.
There's another question.
Yes.
If your theorem could be generalized to reasonable stacks from schemes.
Yes, there's a way to generalize this to reasonable stacks. So, I mean, in particular, yeah, you can generalize this to like Artin and stacks, I think, as long as they're like, QCQS.
Cool.
So yeah, maybe I haven't really explained the QCQS-ness assumption, but maybe if you're interested in this, somehow at the back of this, there's a bunch of ideas from stratified homotopy theory that are being used. But, since I'm not explaining the proofs, well, it's not obvious where they're being used. And one of them is the fact that, there's an equivalence between spectral topological spaces. So those are the topological spaces that are the underlying spaces of QCQS schemes, and pro objects in the category of finite cosets. And somehow this is used to understand various things about constructible sheaves, and that's somehow where the QCQS-ness is used. But I mean, it's possible to remove this at the cost of making things a lot more complicated. So, okay.
Sorry, can I ask one quick question?
Yeah.
Is this B gal S always protruncated, or knows what happens to it?
Yeah, I don't know actually.
So you only know that this map is an isomorphism on protruncations. You don't
know
it exhibits the right-hand side as the protruncation of the left-hand side.
Yeah, I don't know if it's protruncated in general. I think I expect probably not, but well, I don't know. It's also because, like, I'm not sure. Yeah, I guess I'm not sure anyone even knows if, in general, the Étale, the non-protruncated Étale homotopy type, is actually protruncated. Somehow these questions about if something's protruncated seem kind of difficult. Yeah, unfortunately, I don't have something very good to say there. Okay, so here's the theorem. I sort of wrote this before, but let me say it again. So again, S is going to be a QCQS scheme, and the theorem is that there's an equivalence of infinity categories between, on the one hand, constructible Étale sheaves of spaces on S, and on the other hand, these sort of functors extended to pro objects from this just pro ordinary category to pi finite spaces. So that's the sort of non-abelian version, but let me maybe state the abelian version, which is also that for any finite ring R, there's an equivalence between, well, let me write it like this, the sort of derived infinity category of constructible Étale sheaves on R, and the same sort of thing with values in perf R. So usually when you're in the sort of abelian setting, you talk about, you ask for the stocks of the constructible sheaves to be perfect complexes, or, in this case, this just means, compact objects of the derived category of R. Now, what I want to talk about in the remaining 15 minutes or so is how to upgrade this from finite coefficients, which of course are interesting, to L-adic coefficients, which is, somehow often when you're doing things with, Étale cohomology, you care about L-adic coefficients. And this is somehow also known as, how I got some hand in thinking about condensed math. So I want to describe a little bit of this.
All right. So once again, so this is your answer to the question how to get rid of locally constant assumption, right?
Yeah. So yeah. Thanks more. So this is how to get rid of local constancy. And maybe I should say, so it's not completely obvious from this, but from this theorem and some very small other things, it's not so hard to see that if you want to put local constancy conditions on this side, what you can say is functors from here to here that send all morphisms to equivalences. So it also, even in that setting, gives, in some sense, a more simple classification result that that doesn't depend on this Étale homotopy type as a whole. Okay. So yeah, what I want to talk about in the remaining time is sort of upgrading. So the remaining time I want to talk about upgrading from finite to ZL, QL, QL bar coefficients. Okay, and so maybe let me recall something. So classically, how do people work with this like derived constructible category of L-adic sheaves? So what people don't mean is that they're sheaves of ZL modules with that are constructible as sheaves of ZL modules. And part of that is because that definition, I mean, ZL is a topological ring, and that definition doesn't take into account the topology at all. So you want to somehow encode that. And maybe you say, well, ZL is the inverse limit of Z mod L to the n's. So you can just, you define it is defined to be the inverse limit of all of the constructible derived categories of Z mod L to the n's along this sort of, modding out by, well, I guess I'll have to do it like that, along sort of modding out by, another power of L. So this is just tensoring with Z mod L to the n. And so, I mean, this is okay. You can work with this because what are your objects? You're thinking about them as some compatible system of, Z mod L to the n constructible sheaves, along with equivalences after, of modding out by another power of n to the next one. But then what you do is you then pass to QL coefficients by sort of inverting L, and somehow this makes this even more complicated and a bit hard to work with. And so where somehow the condensed math gets put into here is that so as we've been working with it, this functors out of this Galois category, this thing I've been writing as like sort of continuous functors, won't commute with all of these operations. And part of the problem is like, well, if you think about this inverting L as sort of, taking a co-limit of, of the sort of multiplication by L functors, of this category with itself, then I mean, there's no reason why taking functors into that colimit, will allow you to sort of pull the colimit out, unless you had some sort of compactness hypothesis. But it turns out not to be true. But it's sort of fixed if you really include the topologies in some way. So you really need to use the topologies on ZL, QL, etc. And this is what leads you to sort of work with condensed mathematics. So what I want to explain in the remainder of the time is sort of, how you can do that and how you can upgrade this theorem. So in order to do that, I'm going to need to give a quick overview of condensed math. Okay, so the emphasis is going to be on quick. So, it is going to be quite quick. So, this, you could talk about this for quite a long time. So, another remark is sort of, there's some sort of set theoretic issues that you run into with this theory, and I mean, you can treat them in a number of ways, and Clark Barwick and I, treated them in a somewhat different way than Peter Schulze and Dustin Glasman, and the name we use for this is ℓ-adic, which is basically some, as far as I understand, some Greek word that essentially means the same thing. It's used in biology to mean something very similar, apparently. But the point is of this is that this will, this condensed math will allow us to mix topological, and by topological I mean like the topology on ZL or QL, like something that actually is topology, and homotopical structures. Because like somehow working kind of classically, there's not a good way of like, including a topology on a ring when you talk about the derived category of a ring. But in this world, there will be. Okay. So here's the definition. And so I'm going to just tell you what the definition is so you can think about it a bit. And then I'm going to tell you some nice properties it has that maybe will make you believe that you could do some things with topology. and then after that, I'll state the theorem. So so let C be an infinity category with finite products. And so the infinity category of condensed objects of C is defined in the following way. So cond of C is, well, they're product preserving pre-sheaves on a category I'll write as proj to C. So what is this category? So this is an ordinary category, and it's the category of projective objects in compact Hausdorff spaces. And okay, so these guys are also known as profinite sets, such that the closure of every open, so if you take an open set and you close it, then it's still open, which is kind of a weird property. But so okay, this has something to do with topology. There's a lot of reasons to say why this is the right choice. One thing to say is, well, so this condensed objects of the infinity category of spaces, this has kind of two descriptions. It's the non-abelian derived category of these projective topological spaces. So if you're familiar with this yoga of non-abelian derived categories, maybe that seems like a reasonable thing to you. It's also known as pro-Étale sheaves on the point. And this is somehow, you know, from the perspective of Glasman and Schulze, I think how this kind of got introduced. There's another way that it can be described by not just taking these guys. You can, there's a Grothendieck topology on the category of compact Hausdorff spaces, and it's, well, it's hypersheaves with respect to this topology. So this description is a bit more simple, but one thing to say is that there's some set theory that you have to deal with to make this precise. This is, you know, a really enormous category. So you have to do something, you know, to, you know, either take, you know, certain, you know, small enough sheaves or work with universes, and, you know, but that's not going to really be important for how to think about it. So the other thing to mention is that there's an embedding of, you know, essentially most topological spaces you could ever care about embed into here. So compactly generated topological spaces, these embed into condensed sets. And the embedding is really a unidata embedding. You just look at maps from these guys into your space. And the important other point is that you can regard this guy as a condensed category. Okay, so those are somehow from the perspective I've been talking about, those are the important points. So it has something to do with topology. And so what I'm going to do in the next few minutes remaining is tell you, one, you don't have to do it this way, but here's an ad hoc way of defining sort of perf ZL and perf QL in this context. And then just the theorem will be that if you sort of interpret this continuous functors in the appropriate condensed sense, then you get a version of this theorem that allows you to replace things with, you know, perf ZL or perf QL interpreted in this way. Okay, so here's this. So the first thing to notice, and maybe it's reasonable to believe from this perspective, you know, up to set theoretic issues, this is going to be some infinity topos. So there's a notion of constant sheaves. And well, you know, because I'm working with categories, I'm going to talk about constant sheaves of categories. So there's a constant sheaf functor that, you know, as usual, there's a constant sheaf functor that's left adjoint to global sections. In this setting, it happens to be fully faithful. So you can regard any ordinary infinity category as a condensed category. And okay, so you can then define perf ZL in here as the limit of the constant category at perf Z mod L to the n, interpreted in the usual classical sense. So it's really just you know, compact objects in that derived category. And so this is something that is not constant. But it turns out that this guy, this global sections guy, actually preserves all limits and colimits, you know, up to some set theoretic, you know, issues. And so actually its global sections give you what people usually work with as sort of the derived category of ZL. And similarly, you can define perf QL as a colimit of the sort of multiplication by L functors but now interpreted in this world of condensed categories. So there's a less ad hoc way of doing this, but at least this gives you some definition. And again, this would give you the usual thing. So here's, do you have a question?
Yeah. This colimit that you're taking, are you taking it essentially in small categories?
This one? I'm taking it in condensed categories.
Condensed small categories, sure.
Yeah.
Okay.
Yeah, exactly.
And I guess it's stable because tables are closed until their colimits or something like that.
Yeah, exactly. Okay. So there, you can do this in a less ad hoc way, but for the purposes of this, it at least, you know, shows that this sort of recovers what people classically did. And so here's the sort of theorem 2, and I'll just finish with this because I'm basically out of time, is that again, if S is a QC/QS scheme, then there's an equivalence of infinity categories between constructible, oh, maybe let me write this in the way that I wrote it before. Constructible sheaves on S, but the L-adic sheaves. And on the other hand, functors that respect the condensed structures from this you know, pro-finite category I defined, which it turns out you can regard as a condensed category, to this guy from up here. So this means respects condensed structures. I won't unpack what that means at the moment, just, you know, for lack of time. But then the second part is, well, for the QL and QL bar versions, you know, people, I mean, only really work with this when the underlying topological space is Noetherian, and so you need a sort of qualification on this, but is if the underlying topological space of S is Noetherian, then you get the same sort of theorem. Constructible sheaves with the sort of QL version are the same things as functors from this guy gal S to perf QL that respect these condensed structures. And of course, you can also put a bar here, but I didn't explain what, how to pass from there, but I think you can probably imagine. So that's how, somehow I got into thinking about condensed things, is because it allows you to prove this theorem. Okay.
Thank you very much for your talk. I have a question, but I'll ask first if other people have questions. My mom is coming and worried that she hasn't seen Peter. She doesn't know that no one has seen Peter. Peter, maybe you can show yourself.
Yeah, I can show myself now. Wait, can you see me?
Not really.
Wait 1 second. How do I switch camera?
Yay! Hey, Peter. Okay, now we can thank the existing.
Hello.
But I wanted to ask. So, wait. First, are there other questions?
Sorry, do you have any applications in mind?
Yeah. So yes, there are applications in mind. So I mean, one thing that we have in mind is for understanding certain things about, like, constructing good moduli stacks of constructible sheaves, and relating certain things to L functions. This is one of the applications that we have in mind for this part of the story. For other parts of the story, such as oh wait, can you see my paper?
Yes.
Yeah. So such as this, there are other things that we hope to do. So I don't know what I should call this. Thinking about using this theorem with Eldon Elmonto, we're trying to sort of reproduce and generalize some fiber sequences in Étale homotopy theory, originally proved by Friedlander, using this technology. Though that's, I should say, it's very much work in progress. So, I mean, those are a couple examples, but there are other things as well.
Sorry, you mentioned some result about truncatedness of the Étale homotopy type over finite fields.
Yes.
Can you somehow prove that result using your description of the Étale homotopy type as being of this category?
This is a good question. I've hoped that maybe it's possible to do something like this, though I don't have anything to say at the moment. But this is something I hope. So I mean, one of the kind of interesting things that arises there as well is, so Eschinger also shows, using this sort of like hyperbolic Artin neighborhood type stuff, that the Étale homotopy type of some reasonable scheme in positive characteristic can be written as some finite colimit of one truncated guys, and somehow we thought maybe it's possible to, I don't know, use some of this technology and some techniques with this sort of thing to do this. But at the moment, I don't know how to do this.
Thank you.
Okay, so may I ask, so in the very end, you said how to define perf of ZL and QL, and I was a bit surprised that you said that both things give the right thing when you take global sections, but how come? So this means that your construction, so the junction works well with both limits and colimits, which was surprising for me. So how do you manage?
Yeah, so yeah, I can describe this. So let me switch my camera so I can see what I am writing. So yeah, so this is kind of a matter of set theory actually, but I think for this particular thing, the sort of set theory shouldn't matter. But the sort of point, excuse me, and let me just do the sort of spaces version, and then you can get the categories version. But yeah, the point is that you have these condensed say spaces. You have the global sections functor. You have the constant sheaf functor. Spaces, and then yeah, somehow the point is that, okay, modulo some set theoretic things, there exists an adjoint here, and what it does is it will send x to the functor that sends let me see if I got this correct. I think I want to say it sends p. So this will be one of these, weird type of topological spaces to the product over the points of P, but just like the underlying set of this guy of X.
So is this like the set with the indiscrete topology?
Yeah, it's like the set with the indiscrete topology. So often we think of this as sort of the this is thinking about your objects as discrete objects, and this is sort of like indiscrete objects, which is, yeah, it's kind of weird, but yeah, basically because of this, well, yeah, this has to preserve limits and colimits. So it's sort of surprising that the underlying things of these actually produce the correct things, but they do. But part of the point of this, though, is that, well, yeah, what this means, is something somewhat complicated, but somehow this guy is compact enough to pull out the sort of colimit. Yeah.
Sorry, what's a condensed structure on Gal-S? Maybe I missed this.
Oh yeah. So this is actually a bit of a complicated story. So I didn't describe this, but so part of there's something kind of annoying about this story. So there's a huge technical amount of work that you have to do to prove this, and yeah, so there's something kind of interesting about this. So how you might try to do this initially. So interesting. So this will not sort of directly answer your question, but it's related to, because the answer is a bit long, but it's related to how you can answer this question. So so here's an interesting aside. So let's just work with condensed sets for the moment. And so these guys, you can describe in a different way than what I did as sheaves with respect to something called the effective epimorphism topology on the category of pro-finite sets. So they're sheaves of sets. the point of this is just I wanted to say that there's some natural embedding of profinite sets into here via the unidata embedding. And so you might think that, so I mean, usually how you embed, objects into some category that allows you to extend the embedding to pro objects is you need the objects to be co-compact. But it turns out that this is false. So what you might try to do is to give this condensed structure on this gal S is it's some sort of pro category. And you might think with some finiteness hypothesis, and what you originally hoped to do is just sort of embed the finite guys in via the constant, sheaf functor, and then, hope you can extend to embed the category pro objects by just checking that things are co-compact. But that's not quite true. So you have to actually do something somewhat complicated to get this in here. But so I'm going to punt a little bit on your question. But maybe something to say is it's related to this work of Jacob Lurie on ultra categories. So somehow it's a bit complicated. So that's a bit unfortunate, but yeah.
Mm. Okay, thank you.
Are there more questions? Or if yes, maybe you can ask them to Peter.
Sorry, do you think that it makes sense to extend your formalism to some other topologies, maybe with some extra structure somewhere?
Yeah. So yeah, definitely. So here's something. Let me write something down. So okay. So here's something pretty interesting. So this is one way of dealing with other topologies. But it has I don't know. I don't know how to prove the theorems with this, and it's also very complicated. So Lurie proved that there is an embedding here's where this QCQS-ness comes in. So we're doing something, somehow fundamentally with the Étale topos of a scheme. And the Étale topos being, or like the scheme being QCQS is equivalent to a property of the topos, and it's called being coherent. So he proved that there's an embedding of coherent topoi, which you should think about as being, coherence is basically QCQS-ness into condensed categories. But it's a bit complicated, but why it's related to other topologies is because, essentially whatever your favorite topology is, the corresponding topos being coherent is equivalent to the scheme being QCQS. So this is true for like the Nisnevich topology, the Zariski topology, the Pro-Étale topology. So it gives you a home where you can talk about both, some sort of, object that is akin to this gal S, and also these sorts of, things that allow you to talk classify, like perf ZL and perf QL and things like this. However, this uses some sort of complicated stuff, uses stuff about ultra categories, which are some sort of thing from logic that are quite complicated, and I can't say I understand them very well, but somehow we were able to get away with not using that stuff. And one of the reasons is because in the category of points of the Étale topos, somehow, endomorphisms of a point are always equivalences. But this is not generally true, for other topologies. But really using this fact was what allowed us to use sort of ideas from stratified homotopy theory to prove these theorems. So yeah, I don't have a good answer for, doing this for a lot more general topologies, unfortunately.
Okay, people, I have a suggestion. How about we do start a coffee break, just because in case some people are tired. And if you want to ask Peter more questions, just write to Dennis and he will put you in the same room as Peter, and Peter won't be able to run away from your questions. And
but
let's
actually,
start.
I need to, I actually need to go.
Ah, he will run away. Well,
so
okay.
Yeah, I apologize, but well, I will be back eventually, but I need to, I need to pick up my partner from their work. So they will be mad if I do.
I see. Okay, so let's start the next talk, if Elton doesn't mind, at sharp, not at 1:45. So like at what time is it in Germany? I don't know. 7 p.m. German time. Okay, and then let's go to coffee breaks. But before, let's thank Peter again. Thank you for the talk very much.
No, thanks.